some recording that, and let me do one more thing. All right, let's begin. So let me share my OneNote. I will have my camera turned off only because I'm using a tablet, and if I go like this, you'll just see my ceiling. So I'd rather not spend energy or internet or you're looking at the ceiling. I will be keeping an eye on the chat. So if you have a question and you're not comfortable talking or you don't have a microphone, that's okay. Make sure that you write typing, like literally the word typing on the chat before you write your question. So that way I could wait for your question to come in and not move on to another problem. And let's begin. So the first problem on the example final asks us to evaluate the following integral. That integral is the indefinite integral t times e to the t dt. Now here, the first thing you have to realize is that t is a linear function by itself. And e to the t is an exponential function. Those are the first two things that you should notice. Now, because t and e to the t are both functions and they are being multiplied together, when we do this problem, you will have to use integration by parts because we have two functions that we have to integrate at the same time. So because of that, we will be using the integration by parts technique. Now, if you don't remember the integration by parts formula, it is the following. It says that the integral of u dv is equal to u times v minus the integral of v du. That's right, Richard, integration by parts. So here it's important for us to realize what u and v are. So you have to let one of these functions be u, and the other one be v. It doesn't matter necessarily which one you let be u or v, but you will notice that if you select the wrong one, even though it doesn't matter, one of them will make you do more work than the other. For this particular problem, I am going to let u be t. That forces v to be e to the t. And at the same time, I'm going to find out what the derivative of u and v are, because I will need them. Now, the derivative of u is just t, is just 1. And the derivative of v, which is e to the t, is just e to the t. Now, let's put this together. So we have the integral of t e to the t dt is equal to, by integration by parts, u times v, so u is t, times e to the t, minus the integral of v du, but we just said that v is e to the t, and du is 1 dt. So e to the t times 1 is just e to the t. And now we have that this is equal to t e to the t minus the integral of e to the t dt. We have a second integral here. Because we have another integral, this is actually an easy integral, but if it wasn't as easy, you will do another u substitution. So because we already used the letters u and v, I will use the letter s. You will let s be t, and ds is just 1 dt. But we already have 1 dt there because dt is already present. So this is just e to the s, and then you can take the antiderivative. And I'm only saying that because this could be more complicated than just e to the t. This could be something like e to the 2t, e to the 3t, e to the 4t, something like that, where you will have to use a u substitution and divide both sides of this equation. But we know that the derivative of e to the t is just e to the t. So the antiderivative of e to the t is e to the t. So this really becomes t e to the t minus e to the t plus c. And don't forget the plus c. You will lose points if you forget to add that constant of integration right here. And that's the end of that problem. It is probably one of the easiest problems on the exam, provided that you know how to use integration by parts. Saying that something is easy is very relative. So I'm saying it's easy, provided that you know how to use integration by parts. That you remember what that technique is and how to use it. Any questions on that? Before we move on to problem number 2. Just trying to get myself some more space here. Let's move this over there. More on this side for now. All right, seeing no questions, I'll move on to problem number 2. So problem number 2, we have to evaluate the following integral. Now, this is a definite integral, and we have to simplify as much as possible. Now, your first method of integration that you should always try is u substitution. So we have the integral from 0 to pi over 2 of cosine of x over 1 plus sine square of x dx. Typically, you will, on most problems like this, you will let the denominator, the entire denominator, be u. But this is what happens when you allow the entire denominator to be du. If you allow the entire denominator to be u, then du, the derivative, is going to be 0 because the derivative of 1 is 0, plus here you have to use the chain rule, so it's going to be 2 times sine of x times cosine of x if you use the chain rule. I'll do that on the side if in case you don't see it. So this on a side. If you have sine square x, you could write it like this with the square on the outside, and now you could use the chain rule. So this is equal to 2 sine of x times the derivative of the inside. The derivative of sine is cosine of x. Right. So this is by using the chain rule. But here, in this problem, I do not have 2 sine of x or cosine of x. I only have 1 cosine of x. And I'm not allowed to substitute variables inside, only constants, right? So I cannot say, okay, let's divide du by 2 sine of x, and then I get cosine dx. That's not allowed. So the u substitution, allowing u to be the entire denominator, does not work. So we have to go back to the planning board. So what if instead of me letting u be the entire denominator, what if I allow u to be sine square x by itself? What happens then? Well, we already know what the derivative is. It's still going to be 2 sine x cosine x. And for the same reasons, it doesn't work. So one thing that you could do is you could allow u to be simply sine of x by itself. If you allow u to be sine of x, then the derivative of u is going to be cosine of x dx. And notice that we do have here a cosine of x dx. So we could do a straight substitution if we allowed u to be sine of x. And if we do the substitution, we'll get the following. We get the integral of 1 over 1 plus u squared dx. The u gets squared because the sine was a sine square x. And I'm only substituting sine of x by itself, not sine square of x. Now, if you notice, I didn't add the limits of integration here. The reason why I did that is because I'm not going to, first of all, this integral and this integral are not the same, right? Because I did a substitution. So the limits of integration are not the same. Now, what you could do is you could actually figure out the new limits of integration by plugging in for our u. So if you wanted to figure out what the lower and upper limits, the new lower and upper limits are, you will say, okay, the old lower limit was 0. So let's plug in 0 for sine of x, because that's what our u is. Sine of 0 is actually 0. We know this by the sine wave. It begins at 0. And sine of pi over 2, if we look at pi over 2, so this is 2 pi, pi over 2 is at 1. So sine of pi over 2 is 1. So our new limits of integration is 0 and 1. Now, you actually don't have to do this step if you if after you do the integration, you bring back your sine of x, then you could use the old limits of integration. But if you wanted to do the problem straight up without bringing back sine of x until the very end, or not at all, then you could use these new limits of integration. The other thing that you should notice here is that this integral is a special integral. It's actually a very special integral. It is one of the integrals that has to do with the inverse trigonometric functions. In particular, this integral has to do with the antiderivative of tangent, of arctangent, actually. So when we compute this antiderivative, we get the following. We get that, and let me just give you the antiderivative for arctangent so you could refresh your memory. So as this an aside, the integral of 1 over a squared plus u squared du is actually equal to arctangent of u plus c. So this is one of the rules of integration that you learn throughout the semester. And this problem in particular actually has that form. This is actually u over a. I'm missing the a here. U over a. Any questions on that one? You should have seen this before, this rule. So I'm going to apply the rule now. So here in my integral, my new integral that has a substitution, a is equal to 1, and the u is equal to, well, u squared, or just u. Now, but what is u originally? U is sine of x. That's the original substitution that we did. So u is actually sine of x. So when I complete this problem, I'm going to have, I'll actually move this over. Let's see if I can move that over. Yeah. Nice. So when I complete this problem, what I have here is I have the integral from 0 to 1 of 1 over 1 plus u squared du, not the x, du. And this is now equal to arctangent of u over a plus c. But arctangent, u we know is sine of x. A we know is 1. We get it from here. Plus c. And now what I could do is I could actually evaluate this integral by using the fundamental theorem of calculus. Because now we have brought back sine of x into the picture, we could actually evaluate this from the original limits of integration from 0 to pi over 2. And we could use the original limits of integration. And what we get is we get arctangent. Before I write arctangent, remember that the fundamental theorem of calculus says that to evaluate a definite integral, you do f of b minus f of a. So that's what I'm going to do now. I'm going to plug in b, which is pi over 2, into sine of x, and 0 for x in sine of x as well. So we get arctangent of sine of pi over 2 minus arctangent of sine of 0. Sine of pi over 2, we know is 1. We actually calculated that earlier. So we get arctangent of 1 minus arctangent of 0. And I am actually going to leave the problem up to here. You could actually compute this a little bit more because you could find out what arctangent of 1 and 0 are by just using trigonometry. You could use the fact that you could rewrite this as tangent of theta equals 1 and solve for theta, and you could write this one as, tangent of theta equals 0 and solve for theta. If you know that the tangent is sine over cosine, you could even use those techniques as well. But I'm going to leave it like as this. If you want to actually compute this, is not too difficult, but I trust that if you're in calculus 2, you should be able to do that much on your own. So sine theta over cosine theta equals 0. So you could figure this out as well. Any questions on this problem? So the difficulty in this problem is actually remembering this rule right here. Okay, there's two more of these that you have to remember. You have to remember arcsine, and I believe the other one is arcsecant. And they have to do when you have a squared minus u squared, and when you have the square root. Yeah, actually both of those have the square root. And it's just the order that changes. So you have square root of a squared minus u squared, and then square root of u squared minus a squared, and then times u. So if you don't remember this is something that you should definitely go back and review, because a problem like this is going to be on your final exam using one of those three rules for integration. Any questions before I move on to problem number 3? Alrighty, seeing none, I will continue. For problem number 3, we are given some information. So we are told to use the fact that cosine square of theta is equal to 1 plus cosine of 2 theta over 2 in order to evaluate the integral given. That is a definite integral. It's a definite integral from 0 to pi over 12 of cosine squared of 3t over 4 dt. Now, in this problem, we're given some information. This is actually, this is the power reducing formula for cosine. So this is power reduction, which you should have learned in trigonometry. But you're given this in the problem, so you don't have to memorize this, which is a good thing. Now, we have this integral. We have the integral from 0 to pi over 12 of cosine squared 3t over 4 dt. For this problem, we have to use this fact. The reason why they gave us this is because we have to use it eventually. So one of the things that you have to realize is that you have to make this look like cosine squared theta by itself, with nothing else in the denominator and nothing else on the inside. So before we take the integral, what we're going to do is we're going to rewrite cosine squared 3t over 4 so that it looks like just cosine squared theta. The first thing you should notice is that we could rewrite this as the integral from 0 to pi over 12 of 1 over 4 times cosine squared 3t dt. That's the first thing you should realize. We're allowed to do this. Second thing you should realize is that by doing this, we could pull out that constant. So we could pull out the 1 over 4. So we have 1 over 4 times the integral from 0 to pi over 12 of cosine squared 3t dt. And now we could use a u substitution. So we can let u be equal to 3t, and that forces du to be equal to 3 dt. I don't have a 3 dt here. I don't have a 3 dt on the outside. I have it on the inside, of course, but not on the outside. So let's divide both sides of this by 3, and I get 1/3 du is equal to dt. I'm going to substitute 1/3 du for dt, for this dt. And what I will get is the integral 1 over 4 times the integral of from 0 to pi over 12 of cosine squared u times 1/3 du. That's a substitution. So dt turns into 1/3 du, and 3t turns into u. Now I have another constant here that I could pull out. I could pull out that 1/3. So we get 1 over 4 times 1 over 3 times the integral from 0 to pi over 12. Actually, let me drop this. I don't need this here. We don't need the integral, the limits of integration here. 1 over 4 times 1 over 3 times the integral of cosine square u du. We could do this multiplication. This is just going to be 1 over 12 times the integral of cosine square u du. And notice that now I can use the given information. I can use the fact that cosine squared theta is equal to 1 plus cosine of 2 theta over 2. So let's use that. So we have 1 over 12 times the integral. Instead of cosine square u, we're going to have 1 plus cosine of 2 theta, or rather 2u here, over 2 du. Now we have used the given information that was up here. From this point on, we could use a few techniques from the course. Namely, we could first rewrite this as 1/2 plus cosine of 2u over 2 du. Simply break up the numerator. And then we know that we could actually find the integral by pieces. We don't have to do it all by once. We could do integration term by term. So we're gonna have 1/2 times the integral of 1/2 du plus the integral of cosine of u, or of 2u, over 2 du. So we could break up our integral like in this way. Keep in mind what u was. U was 3t. Eventually, I'm going to bring that back in. So we have 1 over 12. I'm just bringing that 1 over 12 down, times the integral of 1/2 du is simply 1/2 times u by the power rule. You can make believe that there's a u to the 0 power there. So you add 1 to the exponent and 1 to the denominator. So this is simply u to the first over 1, or just u. So we have 1/2 times u. Here we could pull out the 1/2. If you wanted to, you could write this as 1/2 times cosine of 2u. And to take this integral, we have to once more use a substitution. So let v now be equal to 2u. dv is going to be equal to 2 du, which means that 1/2 dv is equal to du. Notice that in this problem, I now have to use 2 substitutions to solve this. So what we really have is we have 1/2 times the integral of cosine of v now times 1/2 dv. This 1/2 comes from this substitution here. But I could pull that 1/2 out. So when we do that, we have 1 over 12 times 1 over 2u plus 1 over 2 times 1 over 2. It's just that this 1 over 2 is that 1 over 2 that I just pulled out, times the integral of cosine of v dv. So this problem is there's a lot of bookkeeping in this problem. You have to be very careful to not make a mistake. Take each line one step at a time. So we have 1 over 12 times 1 over 2u plus 1/2 times 1/2 is 1 over 4. And the integral of cosine of v dv is sine of v plus c. You have sine of v. And I'll throw in the plus c at the end here. Now, remember that this was a definite integral from the beginning. So that plus c is actually going to go away. Because you actually know how to find the plus c, because we have the limits of integration. So let me remind you of something. So u, we said, was equal to 3t. V, which we use up here, was equal to 2u. So those are the substitutions that I made that we have to bring back in eventually. And this is the step in which we're going to bring them in. So this is equal to 1 over 12 times 1/2. U was 3t. So let's bring that in. Plus 1 over 4. And v was 2u. But remember that u was actually 3t. So I could just bring that in right away. And plus c. Actually, let's drop the plus c because I actually will be evaluating this because we have the limits of integration. So the limits of integration originally were 0 to pi over 12. So eventually we're going to evaluate this using the fundamental theorem. So we have 0 to pi over 12. So we're writing this from 0 to pi over 12. We're almost done with the problem. So we have 3 over, when you multiply 3 over 2, and then you multiply by 12, we get 3 over 24. Okay, so 1/2 times 3 is 3 over 2, and then 3 over 2 times 12 is 3 over 24. So we have 3t over 24 plus 1/4 times 1/12 is 1 over 48. And then you bring the sign of 2 times 3, which is 6t. And we're evaluating this from 0 to pi over 12. 3 over 24 actually simplifies. This simplifies as 1/8, 1 over 8. So we get t over 1 over 8, t over 8, not t over 1 over 8, t over 8, plus sine of 6t over 48. You could combine the fractions here. You could write 8 as 48 by multiplying by 6. So you can multiply the left side by 6 over 6 and times t over 8 plus sine of 6t over 48. Then we get 6t plus sine of 6t over 48. And you're going to evaluate that from 0 to pi over 12, which is the given. And that will be the last piece of the problem. So by the fundamental theorem of calculus, you're going to do f of b minus f of a. So that means you're doing 6 times pi over 12 plus sine of 6 times pi over 12. Right, you're substituting wherever you see a t, you're substituting pi over 12 over 48. I'll answer that question after we finish this, but because I'll have to think about it. And we have here minus 6 times 0 plus sine of, so this is minus 6 times 0 plus sine of 6 times 0 over 48. This whole piece is just equal to 0, so we don't have to worry about it because 6 times 0 is 0, sine of 0 is 0, so 0 plus 0 over 48 is 0. So that whole piece is going to go away, and we just left with pi over 2 plus sine of pi over 2, which by the previous problem we know is 1 over 48. Over 48. So this is equal to just pi over 2 plus 1 over 48. You could simplify this a little bit more if you wanted to. You could get rid of the fraction in the denominator by just combining using the LCM and then combining, but this is his final answer. So Richard has a question. He says, can't we just use the power reducing formula instead of using u sub after we move the 1/4 outside of the integral? You mean all the way up here in this step? You cannot. And the reason why you cannot is because the power reducing formula says that you have to have 2 theta in there. And we have 3t. Not 2 theta, theta by itself, not 3 theta. So you first have to rewrite the whole cosine squared to look like theta. So you have to use the substitution first. Yeah, those are things that, you know, with some problems, it just so happens that if you do that, it will work out perfectly. It just so happens that it will work out perfectly, but with other problems, it will not. You could do that, Philip. You could do that. You could multiply 2 theta by 3. But I mean, for the finalist, it's not going to be a problem because you're not going to get a problem more difficult than this, right? I don't think you're going to get something like 3t, which is fine. You could say 3 times theta times 2 theta is going to be 6t, which is fine. But if you get something, let's say instead of cosine of 3 theta, you get cosine square of, let's say, 3t plus 5 t squared divided by something else. Now this is a more complicated problem that you'll be forced to use a substitution here. So that's why you have to be careful. The point of this problem is not necessarily for you to just get it right. It's for you to actually follow the procedure so that when you encounter something like this in the future, you know what the procedure is. That's really the point of all of these techniques that we learn. In the final, you're only asked to apply them to the most basic, but taking shortcuts sometimes lead us to bad roads. So I suggest that you just do it the long way, because the long way you could actually figure out any mistakes that you make along the way faster. Hopefully that answers your question. And like I said, you could simplify this a little bit more. The final answer, which I have all the way to the right here. You could combine the fraction and then use the keep change flip method to simplify this more. You could do pi over 2 plus 2 over 2 over 48. And then you're going to get pi plus 2 over 2 over 48. And you can use the keep change flip method to solve this. So this is going to be pi plus 2 over 2 times 1 over 48. And you're going to get pi plus 2 over 96. And that should be the final answer after you simplify. I don't know how your professor will grade you, if they're gonna accept this as an answer, or this is an answer, or this is an answer. But if the simplification is easy enough, you should do it. But just be careful when simplifying, because I see a lot of students who actually lose a lot of points because they don't simplify correctly, even though they did all the problem right. At the end, you miss a step here and there on the simplification, and then you lose a bunch of points. So just be mindful of that. That's problem number 3. Somewhere here, I have problem number 4. Just right up here. Let me bring it down. In problem number 4, we're given some more information. And in fact, this is the other inverse trig technique that we had prior, that I mentioned prior. And then there's arcsecant that you can also find. I believe it's arcsecant for the other problem. So here we're told that we're given another fact, which is really good that you're being given this information, because that way you don't have to memorize it. You just have to use it. So you're using the fact that du over the square root of a squared minus u squared is equal to arcsine of u over a plus c in order to evaluate that integral. This is an indefinite integral. You're given 5 over radical 9 minus 4x squared dx. One of the first things that you should do is definitely pull out that 5. Okay, let's get the 5 out of there. So you get 5 times the integral of 1 over radical 9 minus 4x squared dx. Here you could let u be equal to, u squared be equal to 4x squared, and you could let a squared be equal to 9. I'm giving the answers before I even do it. You could let u squared be equal to 4x squared and a squared be equal to 9, because this has to be of the form a squared minus u squared. And that also forces a to be 3 and u to be 2x. Here we're only really concerned with the positive answer, not with the negative. So that's why I'm not writing plus or minus 3, plus or minus 2x. But proper, you should write it like that. So now we actually know what this integral turns into. So this whole integral that I have here on this side will turn into arcsine of u over a plus c. So we have 5 times arcsine of u over a plus c. But now we know what u and a are. U is 2x, a is 3. So we get 5 times arcsine of 2x over 3 plus c. And when you distribute the 5 in, you multiply both of these by 5, you get arcsine, 5 arcsine, of 2x over 3 plus c. When you multiply the c by the 5, you could just assume that's just another constant. So you could just condense it as just 1c. And that's the answer for this problem. This is actually one of the easiest problems on the test. Are there any questions on this one? I think actually I have one slight mistake here. Something that you shouldn't forget because I forgot it and you should not forget it. You have to find the u, which is 2, and then bring that in. So you just have to multiply at the end by, so you have 2dx, so you have to multiply at the end by 1/2. So that 1/2 equals 2dx. Because you do the substitution for a and u, you also have to not forget to do substitute for dx. So we have 1/2 du. So this is actually 5 over 2 throughout. Do not forget that. It's easy to forget that. It's easy to forget that dx is part of one of the things that you have to substitute by. So when you find u, find du right away. So far, the first 4 problems of this exam are really straightforward. It's mostly computation. For 2 of them, you're given information that you have to use. And for the first 2, you just have to remember some information like the improper integral technique, not improper integral, integration by parts, and one of the 3 inverse trigonometric integrals. For problem number 5, we move into more of the geometrical part of the course. So for problem number 5, we have to sketch a region in the xy plane that is bounded between the graphs of y equals the square root of x and y equals x squared. We're asked to set up the integral and not evaluate it. So we have to, all you have to do is really set this up. We don't have to do anything else besides that. Let me just move this down to give myself some more space. All right, so for this problem, we have to sketch some region in the xy plane. So I'm going to really quickly draw my xy plane of x, y. Now I'm told that I need to graph y equals radical x and x squared. And then I'm asked to set up an integral that computes the area of that region. Now y equals radical x, it's a function that looks like this. Y equals x squared, it's a parabola that looks like this. If you notice, there are points at which these 2 functions intersect. They intersect at the origin and at whatever this point here is, which we could actually find. And the area that we're interested in finding is the area that's trapped in here, this blue piece. So we have to set up an integral that gets us that area. The way that you set up the integral is you look at the function and you think about, height, the height of the function. So the integral really, the way that I choose to remember this is as follows. Typically, you're going to have a top function, your top function, minus the bottom function. dx. That's the way that I choose to remember this when I do this type of problems. And when I say top and bottom, we are talking in relationship to the x-axis. So if I'm looking from the x-axis going up from here to here, which one is on the top, the red one or the blue one on that interval where the region is? The red one is on top. So the top function is going to correspond to radical x. And the bottom function is going to correspond to x squared. And that's how you set up this type of integrals. You think about which functions on the top of the region and then which functions in the bottom of the region. We're not done though, right? This integral is an indefinite integral. To find the area of that I just enclosed, we need to find a definite integral. So we have to find out what the limits of integration are. So we just said that our integral is going to be radical x minus x squared dx. Fine, perfect. But how do I find out now my limits of integration? Well, the limits of integration will occur where the endpoints or the graphs intersect. We already know one of them. That's the origin. We just have to find the upper limit of integration. To find that upper limit of integration, all we have to do is set these two equations equal to each other and solve. So when is radical x equal to x squared? That's the question that we're asking ourselves. When do you think that they're equal to each other? There's only two numbers that will answer this equation for you. If you want to, you could move things around.
1 and 0.
But there's only two numbers that that makes this equation true. That's right, 1. If you take the square root of 1, you get the same thing as 1 squared, which is 1. So 1 is equal to 1. And that's your integral. And that is the solution for this problem. We don't actually have to evaluate the integral. There's no need to actually evaluate it. We just have to set it up, and that's it. So if you think about which function is in the top minus which one is in the bottom, you get the area enclosed. And all you have to worry about again is the actual limits of integration. You have to find the a and the b here. Are there any questions on this problem? All right. Seeing none, I will continue. Problem number 6 is a continuation of problem number 5. It asks us to set up an integral that computes the solid obtained, the volume of the solid obtained by revolving the region that we just did in the previous problem about the x-axis. So let's redraw our picture from before and see what we get. So from before, we had this region, right? We have x, y, and we have the region looking like this. We had y equals radical x looking like this, and x squared looking like this. Now we know our limits, or where they intersect. Where they intersect at 0 and at 1. And again, the interesting piece of information is this area enclosed here in the green. But now this problem asks us to find, well, not to find, but to write the integral that will give us the volume when we revolve this picture about the x-axis, when we bring it down. When we bring that down, what are we going to have? We're going to have something that looks like this and something that looks like this. And the volume generated corresponds to this region. Here, we will use, because we're returning out the x-axis, we will use the this method. Okay, we'll use this method. We have two curves defined in this region. We have two curves defined in this region. We already know what those curves are because they're given in the problem. We have radical x and x squared. How do you find what the region is? We use, again, the disk method. What does this method say? Does anybody remember? The disk method says that when you're revolving some area about the x-axis or the y-axis for that matter, you get that volume by doing pi times the integral from a to b of, and I'm not going to write it the way that the book writes it. I'm going to write it in the following way. You have the integral of a to b of the outer radius squared minus the inner radius squared dx. What is your outer radius here? The outer radius, when you look at it, is what ends up on the outside. What ends up on the outside when we revolve? These red lines end up on the outside, and the blue lines end up on the inside. Right? This is my outer radius, my inner radius. If you think about it as let's say as a half circle, if you think about it as this, when you draw the other half circle on the other side, this piece is the one that's outside. And for this particular problem, this sharp piece is the one that's inside, the inner one. So that's what's happening here. Even though we have some open spaces here where, there is no area, the blue line is clearly the one that's on the inner side. It's closer to the axis. And the red one is further away from the axis. It's the outer one. So when we use this method for this problem, it actually comes out to be the same as the previous problem with a little caveat. Now we are squaring each of the functions. So what we get here, as far as the volume, is we get pi times the integral from a to b of square root of x squared minus x squared dx. We actually do know what a and b are because we did it in the previous problem. That's still 0 to 1. So we could actually substitute that in right away. So we get pi times the integral from 0 to 1 of the square root of x squared. This you could think about it as x to the power 1/2 to the 2 minus x to the 2 to the x. Here you could multiply the exponents. There's why I rewrote it so you could see that the exponents multiply and cancel. So you're going to have the integral, pi times the integral from 0 to 1 of x to the power 1, because 2 divided by 2 is 1, minus x to the 4 dx. And that will be, this is the integral that gives us the volume when we rotate our area from above, this area right here, and bring it down about the x-axis using this method. You have 3 methods for this problem that you could be asked for, right? We have this method, which is the more likely that you'll be asked to do. You have the shell method, which is second more likely. And then finally, you have the washer method. Actually, the washer method is more likely than the shell method. These are the 3 techniques that you learn in Calculus 2 when it comes to revolving volume or areas to get volume. If you don't remember any of them, I suggest that you review them, especially this method. For this type of problems on the final, typically this method is what's covered. But you should know all 3 of them. And you should know, by the way, that if you're revolving about the y-axis and not the x-axis, you have to remember to change your functions, okay? You have to write them in terms of x and not y if you're revolving about the y-axis. So if you're going in this direction, you have to change radical x and x squared. Okay, so you'll get How do you change them? You simply solve for the other variable. So if you have y equals radical x and you want to solve for x, you square both sides, so you get y squared is equal to x. And for the other one, you have y equals to x squared, you square both sides, you find the root on both sides, and you get radical y is equal to x. And then you'll be, if you're going in the other direction, you'll be using y squared and radical y instead of x squared and radical x. And then you'll be working with dy, and that also will change your limits of integration. So I suggest that you look at problems like this as well. It is not likely that you get something about the y-axis, but in case that you do, you are prepared. Any questions on this? All right, I will take a second to go to the door because somebody is knocking the door. It shouldn't take me more than 30 seconds, and then I'll be back to the number 7. Right, sorry about that. Any questions before I move on to number 7? We're about halfway there, and it only, with the explanation, it's only taking me about an hour, not even 55 minutes. So that's not too bad. It's not the greatest, but it's not too bad. Obviously, I'm explaining things. When you do problems like this on your own, you don't have to explain, so you go faster. This is actually an exam that most of you could probably finish in an hour and a half, especially when you're not explaining things. Alrighty, so the next problem says, evaluate the improper integrals using a limit to compute their value or to show that they diverge. The problem number 7a, we have the improper integral from 1 to infinity of 1 over radical x dx. Now, there are two types of improper integrals. There's a type 1 and a type 2. On the exam, it's very rare to see a type 2 integral. You typically only see type 1. Now, why is this an improper integral? This is an improper integral because one of the limits of integration is infinite. If you check the lower limit of integration, if you plug in 1, you're just gonna get the integral. You're just gonna get 1 over square root of 1, which is just 1, and that's not an issue in the domain. So we could move on with our integration techniques for improper integration. Now, before we write the definite integral using the substitution of the limit, let's first calculate the indefinite integral of 1 over radical x and see what we get. If we don't involve the limits of integration, let's see what we get. So we have the integral from 1 over radical x dx. That's going to be equal to, I'm going to rewrite it as the integral of x to the power negative 1/2 dx. Right? This is an easier way of doing it. Now, here we could use the power rule. The power rule says that when you have x to some power and you find the antiderivative, you add 1 and then divide by the new power. So we're going to have x to the minus 1/2 plus 1 divided by n plus 1, but n here is negative 1/2, so we're going to have negative 1/2 plus 1. That's by the reverse power rule. Now, minus 1/2 plus 1 is just 1/2. So we get x to the 1/2 on the numerator and 1/2 in the denominator. This is a complex fraction. This is x over 1 to the 1/2 divided by 1/2. So we could use the keep change flip method. So we have x over 1 to the 1/2 times 2 over 1, right? We keep the first fraction the same. We change the sign from division to multiplication. And then we flip the second fraction. Instead of 1/2, I'm going to multiply by 2/1. And you can see that this becomes 2 times x to the 1/2 plus c. Because remember that plus c, we were taking an antiderivative. And you could simplify that a little bit more. You could bring back the square root, and that will be what the indefinite integral is. So it's good to have an idea of what the indefinite integral is before we go to find the definite integral using the techniques for improper integration. So let's actually now compute this using our improper integration techniques. First of all, we have the improper integral from 1 to infinity of 1 over radical x dx. We know that that is equal to, we're allowed to substitute instead of infinity, we're going to let b be equal to infinity. So we're going to have the integral from 1, well, first of all, we're going to take the limit as b goes to infinity of the integral from 1 to b of 1 over radical x dx. We already computed what this improper integral is. That's why we did that work before, right? We know that that's going to be 2 times radical x. So this becomes the limit as b goes to infinity of 2 times radical x. And we're evaluating this from 1 to b, right? Because it's a definite integral now. So we don't need the plus c. By the fundamental theorem of calculus, we're going to do f of b minus f of a. So we're going to have limit as b goes to infinity of f of b. B is just b. So we're going to have 2 radical b minus limit as b goes to infinity of f of a, which is 2 times square root of 1. Now, I'm going to do the second part first, this part. 2 times the square root of 1 is just 2. The limit of as b goes to infinity of 2 is just 2 because there's nothing to plug in there. There's no b's. So this whole piece is just 2. We have the minus sign that carries over, so that's minus 2. On the front piece, we have limit as b goes to infinity of 2 times radical b. So what we get is 2 times radical infinity. You could actually think about what you get when you plug in infinity here. When you plug in infinity, or when you begin plugging numbers for b as b goes to infinity, this whole thing goes to infinity, right? This whole thing, 2 radical b, goes to infinity as b goes to infinity. And the minus 2 is negligible. So this shows that the improper integral diverges because it doesn't approach one particular number. This diverges. For the integral to converge, our result should have been a constant. But instead we got infinity. So we know that this indefinite integral diverges. Notice what I did here in this problem. I first found out what the indefinite integral is. The reason why I did that is because it's easier to figure out what the indefinite integral is right away than dealing with the limit substitution and the limiting process. If you do the indefinite integral first, then when you begin doing the improper integral, you can right away substitute and find the limit. And then this becomes a 2-part problem. Find the indefinite integral, and then find the limit when you apply the fundamental theorem of calculus. Any questions so far on this problem in particular? All righty, not bad. Now part B, so there's a part B to this problem, which is right up here, and it looks very tiny right now. Part B says to also find the improper integral using a limit to solve for the improper integral from 0 to infinity of e to the negative y dy. So here we have, I'm going to do it down here. We have the improper integral from 0 to infinity of e to the negative y dy. Again, you should always check that you have a type 1 or type 2 indefinite integral. How do you know if you have a type 2 indefinite integral? If when you plug in one of the limits of integration, in particular the lower limit, or even if you don't plug in the lower limit of integration, if you have any number in the domain that makes your function here undefined, then you know you have a type 2 indefinite integral. You should not be having issues in the domain if you have a type 1. So if you plug in 0 here for y, we get, let's just plug in 0 for y here real quick. Plug in 0 for y. We got e to the minus 0, which is equal to 1 over e to the 0, which is equal to 1 over 1, which is 1. 1 is a real number, so this is a type 1 improper integral. Richard said it's going to be 1. Very good. So now we could go ahead and again use our techniques to solve this. Now, again, let's start by just solving the indefinite integral of e to the y dy. If you let u be negative y, then du is going to be equal to negative dy. So that means that negative du is equal to dy when you divide both sides by the negative 1. So our substitution becomes the integral of e to the u times negative dy, times negative du, I mean. And then when you multiply the negative, you could keep the negative on the outside if you want to. You have the negative e to the u du. The antiderivative of e to the u is e to the u. So you have negative e to the u plus c. But u was negative y, so we have negative e to the negative y plus c as the solution to the improper integral e to the negative y dy. Now, when we go to solve the improper integral from 0 to infinity of e to the negative y dy, we could again let b be infinity, rather. And then you have the limit as b goes to infinity of the integral from 0 to b of e to the negative y dy. We already know what this integral is. This becomes the limit as b goes to infinity of this negative e to the negative y. Negative e to the negative y. And we're going to evaluate this from 0 to b. Now, we're going to use the fundamental theorem of calculus, which says kind of compute f of b minus f of a. And we have the limit as b goes to infinity of negative e to the negative b minus, just write it like this, minus e to the negative 0. So I choose to write like this time. So that gives us the limit as b goes to infinity of negative e. Let me actually just, let's do it like this. Negative e to the minus b, minus and minus is plus, we get plus e to the 0 here. E to the 0 is 1, so we get limit as b goes to infinity of minus e to the minus b plus 1. And then finally, you fix this negative exponent, you have limit as b goes to infinity of negative 1 over e to the b plus 1. As b goes to infinity, notice that e is not in the denominator. As b goes to infinity, this fraction goes to 0 because 1 is a constant, but b is increasing. So this whole fraction goes to 0, and you get plus 1, so we get 1 as a solution. So this shows that the improper integral converges to 1. So this shows that the improper integral, which was the integral from 0 to infinity of e to the minus y dy, converges to 1. Again, how do we know that it converges? We know that it converges because when we computed the limiting using the limiting process, we got a number, we got a constant, we got 1. That number could have been 2, it could have been 3, it could have been 1.5. As long as you get a number, you know that you're converging to that number. Again, this is a problem that it's not the easiest. You have to remember some facts about type 1 and type 2 integrals. You have to remember that. You have to remember your integration techniques, obviously. So you have to find the integral. I suggest that you first find the indefinite integral, and then you bring in the limiting process. It makes the work a little bit cleaner. It may seem longer, but it actually makes the work cleaner because you can just focus on the limiting process at the end. Any questions on this problem? Cool. So this problem was about halfway there when it comes to the final exam. So right now you have only to do problems 8, 9, 10, 11 through 15. Now this is where the problems now become a little bit more challenging. Now we are completely out of almost completely out of the integration techniques, and we are going now into computing limits of sequences and showing that they diverge or converge using our convergence test. You have various tests to check for convergence. We have the nth roots test, we have the ratio test, we have the limit comparison test, we have the direct comparison test, we have the ratio test. You have the alternating series test, and you have the I forget anyone. Alternating series test, limit comparison, and Ruth. I think that's all of them. I may be forgetting one, but I think that's all of them. If I forgot one, you guys can let me know. But problems 8, 9, and 10 all deal with convergence of sequences and series. So problem number 8 deals with computing the limit of sequences and showing that they converge. Problem number 10 is using the convergence test to show that the series converge or diverge. Problem number 9 is kind of a funky problem because it uses, that's the one that I forgot, the geometric series test. So problem number 9 uses the geometric series to solve that problem. So for problem number 8, for part A, we have to compute the limit of the sequence and show that it diverges or converges. So here for this one, we have the limit as k goes to infinity of e to the k over k squared. Now, e to the k is an exponential function. K squared is a quadratic function. You should know by just graphing that when you graph the exponential versus when you graph the quadratic, the exponential grows faster. It grows faster than the quadratic. That should tell you before you do any work that you should expect this to be divergent. Okay? Because by the picture, the exponential will go faster than the quadratic. And if that's happening, then that means that the numerator is going to infinity faster than the denominator, which means that you're going to get infinity. Now, we have some rules that we could use to actually show this. To show this, we will actually use L'Hopital's rule, which my marker did not write anything. We're going to use L'Hopital's rule. You could apply L'Hopital's rule when you have indeterminate form. Okay? If I think about the limit, when you plug in numbers that go to infinity in the numerator, this is going to go to infinity. If you plug in numbers in the denominator, eventually that's going to go to infinity because it's growing without bound, which means that we get indeterminate form. which allows us then to use L'Hopital's rule. To use L'Hopital's rule, we are allowed to take the derivative of the numerator irrespective of the denominator instead of using the quotient rule. So the derivative of e to the x, when you take it, is just e to the x, in this case k. The derivative of e to the k is e to the k, but in the denominator, the derivative of k squared is 2 times k. And we still evaluate the limit as k goes to infinity. So we apply here L'Hopital's rule. Okay, so you're applying here L'Hopital's rule. Now, if you compute this limit as k goes to infinity, you still get infinity over infinity, right? Because e to the k again goes to infinity, and 2 times k goes to infinity. It may go to infinity. It's lower because it's linear, but it still goes to infinity. So we have to apply L'Hopital's rule again. So apply it one more time. So apply L'Hopital's rule one more time. If you take the derivative of e to the x, again, you get e to the k. The derivative of e to the k is e to the k. We're still computing the limit as k goes to infinity. But now the derivative of the denominator is going to be 2. And now what we really have here is 1/2 times the limit as k goes to infinity of e to the k. But we know that the limit of as k goes to infinity of e to the k is infinity. So really we have 1/2 times infinity, which is infinity, which shows that this diverges. Okay, so now we know that the limit of the series, of the sequence diverges. So since limit as k goes to infinity of e to the k over 2 is infinite, the original sequence limit as k goes to infinity of e to the x, e to the k over k squared also diverges. Okay, so that's 8a. That was 8a. So for 8a, we use L'Hopital's rule. L'Hopital's rule again allows you to take the derivative of the top and the bottom of a sequence or a function when you have indeterminate form as you apply the limit as the limit goes to infinity. Or when you go to 0, if you have 0 over 0, you also could apply L'Hopital's rule. For 8b, we have limit as n goes to infinity of cosine of n over n. We have limit as n goes to infinity of cosine of n over n. For this limit, we have to be a little clever. Okay, we have to be a little clever. Here, this sequence is going to converge to 0. Okay, this is going to converge to 0. And the reason for that is as follows. The numerator is cosine of n. Cosine of n is bounded. It's bounded by 1 and -1 because the amplitude is 1. Okay, so recall that your cosine function, the basic cosine function wave, goes from 1 to -1, and it goes like this, from 0 to 2 pi. Or it goes back down. But no matter how far you go on the x, no matter how much x grows, you're always oscillating between -1 and 1. So the highest cosine gets is 1, the lowest cosine gets is -1. So the numerator is cosine of n, which is bounded between, plus or minus 1. While the denominator, n grows without bound. right? If you allow n to go to infinity, you have 1, 2, 3, 4, 5, all of those numbers going in for n, but cosine is just, oscillating between numbers that are as high as 1 or as low as -1. It doesn't get higher than 1, it doesn't get lower than -1. So you could think about this limit as n goes to infinity as being 1 over n or -1 over n. Right? The highest you could go is n, the lowest you could go is n, but this limit goes to 0, and so does this one. So we can conclude that this sequence actually converges to 0. So the sequence converges to 0. Okay, so that's something to keep in mind. When you're dealing with sine and cosine, they're bounded. They're bounded sequences. They're bounded functions. They have a maximum and a minimum based on their amplitude. Say you had instead of this problem, say you have limit of n, this n goes to infinity of, let's say, 3 cosine of n over n. That will still be the same situation. Now your amplitude is 3 or -3. You still will be bounded by a constant. The only way that this will change is if you added something here. Let's say you added n squared here. If you added n squared here, then this will be divergent because the numerator is increasing faster than the denominator. That's the way that you should think about this type of problems when it comes to the sequence convergence or divergence. So this is one way that you could see a problem here, or a different type of problem. And in this case, it will be divergent in that case. Finally, for 8c, we just go back up to 8c, we have limit as n goes to infinity of the series from k equals 0 to n of 3 over 2 to the k. So for 8c, we have limit as n goes to infinity of the series from k equals 0 to n of 3 to the 2k. Now, for this one, it is a little bit trickier to see what the solution will be, but we could do a little substitution here. Okay. This is equivalent, this limit computation is equivalent to simply doing the series k equals 0 to infinity, just simply substitute infinity for n here of 3 to the 2k. So that's the first thing that you should realize, that these are actually equivalent. This is going to be an example of a geometric series test, not a p-series. So let's look at what's going to happen now. So here, I have 3 over 2 to the k. 3 has no k's in it. There's nothing involving k with 3. So I could actually take it out. You can factor it out. So you could take 3 completely out of the series computation, and you get 3 times the series of k equals 0 to infinity of 1 over 2 to the k. But now, 1 over 2 to the k is really the same as 1 over 2 to the power k. And the reason why this is true is because 1 to the k is always 1, no matter what k is. So you could just take it out. And now you could see that this piece right here is a geometric series where our r, so this is a geometric series now. This is a geometric series where r is less than 1. Where r is equal to 1/2, which is less than 1. For a geometric series to converge, r has to be less than 1. R is the base. If the base is less than 1, then we are guaranteed for the geometric series to converge. So this geometric series converges, and we know what it converges to. So this geometric series converges, and we know what it converges to. And we can calculate where it converges to. Where it converges to. To calculate where it converges to, you simply use the rule that we have from the theorem for the geometric series test. The geometric series is going to converge to, I believe it's a over a plus r, or actually a minus r. Here our a is actually 1, so we have 1 over 1 plus minus 1/2. The 3 that I have outside, that 3, simply comes from the fact that we're multiplying the series by this 3 up here. But the geometric series by itself converges to this. It's just that we have to multiply by 3 because we factor a 3 out. But this is really 3 times 1 over 1/2. 1 over 1/2 is just 2, okay? 1 over 1/2 is just 2. You could again use the keep change flip method. So this is equal to 3 times 2, which is 6. So we get that this geometric series converges, and we actually found out where it converges to. This is something that you should review if you don't remember the geometric series test, and if you don't remember, once you know that a geometric series converges, you can actually calculate where it converges to. It's one of the few tests that tells us the number that we converge to. The other tests that we have, the p-series test, alternating series test, ratio, direct comparison, limit comparison, none of those actually tell us where we converge to. They just tell us that we converge to a number, but figuring out what number we converge to is actually not easy. Let me just write down the geometric series test for convergence so you have it. So if you know that a geometric series converges, then we can find out what the series converges to by doing the following. So if you have a geometric series of the form, let's say n equals 1 to infinity of, it's supposed to be infinity up here, of a1 times r to the n minus 1, then this is going to converge to a1 divided by 1 minus r. Our a here, I said, was 1 because we factored, if my computer will go up, because we factored the 3 out. So we had a 1 here, 1 times 1/2 to the k, where we don't write the 1. If not, I would have had to put the 3 on top. So I rather factor the 3 completely out. It makes the problem much nicer. Finally, a geometric series converges. Geometric series converges if and only if r, which is the base here, is between 1 and -1. Okay, so not 1, little r here is between 1 and -1. So that's how you know when a geometric series converges. If the geometric series is the base is between 1 and -1, you're guaranteed for it to converge, and you can actually figure out what it converges to by using this rule. Any questions on that? Geometric series are probably the nicest series that we deal with. I personally don't like them, but they're very nice. They behave really nice, and we could actually figure out with only our Calc 2 knowledge what they converge to. Alrighty, seeing no questions, I'll move on to problem number 9, which I think I have up here. So let's bring it down. Problem number 9 is a word problem. This is actually a problem that I asked my students in my quantitative reasoning class, Math 126. You actually don't need any calculus to solve this problem. So here we have, suppose that 300 milligrams of a painkiller is given to a patient precisely at 11 a.m. every day, and only 20% of the drug remains in the body after 1 day, since the other 80% are excreted. The first question, 9a, asked us, what amounts of painkiller are in the patient's body when it's measured right before the next dose is given after 1 day? How do you calculate that? That's right. Do 300 times 1 over 5. 1 over 5 is the same thing as 20%. This is going to give you what? I believe it gives you 60. Because 300 divided by 5 is 60. So we get 300 milligrams remaining after 1 day. How about after 2 days of treatment? How much should remain? How do you calculate the second day? We know that only 20% of the drug remains in the body after 1 day. I agree with 60 plus 12. So you could find out 20% of 60, which is 12. So you could do it various ways. You could multiply 60 by 1 over 5. Again, 1 over 5 is the same thing as 0.20 or 20. And that should give you 12. So after 2 days of treatment, you should have 60 plus, 60 plus 12. Now, how do you actually use a geometric series test to solve this? You use a geometric series to solve this. I agree with Philip, actually. As far as the solution for the second day, you're gonna have 300, because I'm assuming here that another dose is given, right? Another dose is given right before the second day. So after the first day, we only had 60 milligrams left. That's 300 times 1 over 5. Now, after the second day, you should have that same dose given plus what remained from the day before. Correct. Correct. Now you have to use that information to create a geometric series. You have to use that information to write a geometric series. How do you go about writing the geometric series for this? You always begin with the initial value. Right? You have an initial value of 300. Now, you have 300 times what? Every day you're getting a new dose, right? And I'm assuming that new dose is of 300 milligrams. So you have to multiply this 300 by 1. Now, after each day, 1/5 of your dose remains. So you have 1 plus 1 over 5 to the power t, where t is the number of days that have elapsed. Okay, t here, where t is the number of days elapsed. Of days elapsed. And you could calculate that this works because if you plug in 0 for t, actually, oops. I think this is minus, actually, not plus. minus half. No, it has to be plus. Give me 1 second. Let me look at my solution. No. So the way that I did this problem, I did it a little bit different. So the way that I did it as follows. Instead of doing the 300 times 1 plus this, I used it 300 times 1 over 5 to the t, which gives you, this gives you the amount remaining. This gives the amount remaining after t days. And then to this, I will actually have to go back and redo this problem. So I'm gonna leave it here because I assume when I did this problem that you are not receiving any doses afterwards. I only assume that the original dose was going down. So I have to calculate this. So I'll do that later. Once I finish this one, I'll send you the solution. But if I'm assuming now that I'm actually giving another dose, then this will change my problem. So I'll move on, but I'll come back to this one later. I'll send you a solution. But this part is certainly correct when it comes to the amount of substance that remains. You just have to think a little bit more about it. You're welcome to volunteer and answer. If it works, we'll check it out before we move on. Unless, no, it's fine. Anyway, let's move on to number 10. I'll come back to this one. Number 10, I don't think it's 75. You see, we basically, that problem is asking us to find out how much of the substance remains after a long time. So we could calculate easily with 300 times 1/5 to the t, how much has gone down. All we have to really calculate now is the relationship with how much is given per day. I have to sit down and think about it. Because I was thinking 300 plus this, but the issue that has is that it doesn't work for day 1. Because at day 1, then we'll have 600. So I just have to think a little bit more about it. There's one more digit that I'm missing. Unless I do t plus. It's okay. I'll come back to it. Let's go on to number 10 because I don't want us to run out of time and then not finish every other problem. So number 10, it says to use the convergence test to determine if each of the following series converges or diverges. So for number 10, we have the following. We have for A, we have the series from n equals 1 to infinity of radical n plus 100 divided by n squared plus 1. So for this problem, we could use so for this problem, we could use the nth root test. We use the n root test because we have here, this is really the series as n equals 1 from n equals 1 to infinity of n to the 1/2 plus 100 divided by n squared plus 1. What the nth root test says is that if the underlying sequence, this is the underlying sequence, if the underlying sequence converges, then the series converges. We can write it like this. We have, or we could even use the limit comparison. Let me use the limit comparison test. Either one will work fine, but I'll use the limit comparison test. So we have, to show that the series converges, we will use the limit comparison test. And we will compare that sequence, the original sequence or series with, we'll compare the original series, which is, it equals 1 to infinity of square root of n plus 100 over n squared plus 1 with the following series. We're going to compare with the series from n equals 1 to infinity of square root of n over n squared, which is really equal to the series from n equals 1 to infinity of n to the 1/2 over n to the 2. And by rules of exponents, you could subtract the exponents. 1/2 minus 2 is going to give you 1 over n to the 1/2. Or 1.5. So this is a sequence. This is a series that I'm going to use the limit comparison test with. Now, this particular series, as Richard said earlier, this is a P series. This is a P series. And here, P is bigger than 1. And so it converges. Now all we have to do is do the comparisons. So by the limit comparison test, we do the following. We do the limit as n goes to infinity of square root of n plus 100 over square root of n over n squared, which is equal to the limit as n goes to infinity of square root of n plus 100 over, I didn't write the n squared plus 1 here. 100 over n squared plus 1 over n squared plus 1 times n squared over radical n. This becomes now, when you multiply, right, this becomes the limit as n goes to infinity. Here you could FOIL. So you could multiply radical n by n squared, 100 by n squared, so you get n to the n to the 5/2. Yeah, n to the 5/2 plus 100 n squared divided by, again, n to the 5/2. And you multiply here and here, you get n to the 5/2 plus radical n. Now, if you take the limit as n goes to infinity of this, from pre-calculus, we know that if the denominators and if the denominator and numerator have the same degree, the same exponent, then as we go to infinity, the limit of this fraction is really the ratio of leading coefficients. The leading coefficients here is 1. So this is really 1 over 1 or 1. Now, since the limit is positive, we got 1 as the limit. Since the limit is positive, this tells us that our original series is positive. This tells us that our original series has the same behavior as our other series that we're comparing to. Has the same behavior as the comparison series. But that comparison series converge. So they both converge. That's what the limit comparison test tells us. Any questions on that? You could have also used the nth root test, the nth term test originally. So if you go back up here and you just look at the, if you just look at the sequence piece, which is n to the 1/2 plus 100 divided by n squared plus 1. This piece, as n goes to infinity, goes to 0, which tells you that this has to converge. It doesn't. It tells you it does not diverge. So this tells us that, does not diverge. If you use the n term test. Problem number 10b says the following. 10b is the series from n equals 0 to infinity of n squared minus 1 over n squared plus 1. This is actually, if you get something like this on the exam, this is the easiest problem probably on the exam. By far the easiest. Because this one, by the end term test that we just did, is going to diverge. So here, so first of all, this series is going to diverge. Series diverges. We can use the end term test. We can use end term test. Why? Because the underlying series sequence does not converge to 0. So n squared minus 1 over n squared plus 1. This, as the limit of n goes to infinity, this goes to 1. And by the end term test, since the underlying sequence doesn't go to 0, the series cannot converge. So since the sequence n squared minus 1 over n squared plus 1 does not converge to 0, the series must diverge. The series from n equals 0 to infinity of n squared minus 1 over n squared plus 1 must diverge. Must diverge. This is probably the easiest problem in the exam, if you get something like this. So I suggest that you be on the lookout for something like this problem, where you have to use the nth root test, the n term test. Any questions on this one? Righty. So yeah, that problem number 10 is pretty straightforward. You could use the limit comparison test. You could use direct comparison. You could use n term test to figure out whether you converge or diverge. You could even use the root test or the ratio test if applicable, depending on the problem that you have. So you're gonna get at least 2 problems where you have to use 2 different tests to show that the series converges or diverges. The next problem is problem number 11. So problem number 11, which I have somewhere up here, I think. Let me just bring it down. Actually, I have it on the other page. Yeah. The problem number 11 says to find the interval convergence of the following power series. So we're given a power series in this case. And we're even told that piece of information, we're even told to check the endpoints to make sure that the endpoints, that this power series converges at the endpoints. And that power series is 5 times x minus 2 to the n divided by n minus 1. Now, to compute the integral convergence, we're going to compute the following limit. We're going to compute the limit as n goes to infinity of an plus 1 divided by an in absolute value. Okay, this is what we're going to use. Now, we're going to compute the ratio first and then worry about the limiting n behavior later. So let's begin. So we have 5. So an plus 1 is just going to be 5 times x minus 2 all the way to the n plus 1. So we're going to have, let me just write it like this, an plus 1 over an. That's going to be equal to 5 times x minus 2 to the n plus 1 divided by n plus 1 minus 1. That's this piece. The second part is the an part. An is just the original series. So that's going to be 5x minus 2 to the n divided by n minus 1. Just bring this down a little bit more. Okay, so what do we have here? So we have a fraction divided by another fraction. So we could use the keep change flip method. So the first one, we keep the same. So it's going to be 5 times x minus 2 to the n plus 1 divided by, you could simplify here, this is going to be n in the denominator. Instead of dividing by 5 times x minus 2 to the n divided by n minus 1, we're going to multiply by n minus 1 divided by 5x minus 2 to the n. Now, this is something that you can do. Here, we could split this up. So this is 5 times x minus 2 plus 1. You could split this up as follows. You could first cancel this 5's, right? You can cancel this 5 because 5 divided by 5 is 1. And then you're left with x minus 2 to the n plus 1 over n times n minus 1 over x minus 2 to the n. And from the first x minus 2 to the n plus 1, we could factor out one of them. So I'm going to factor out 1 x minus 2 to the n, and I'm left with x minus 2 to the 1. And that's going to be multiplied by n minus 1 over x minus 2 to the n. And this is all being divided by n. Here, you could now see that there's some cancellation. As long as n is not equal to 0, x is not equal to 0, we could cancel this 2 out. And I'm left with x minus 2 over n times n minus 1. Now, you could break this up as with the n's on one side. So let me write this as n minus 1 over n, like this. So this whole multiplication, so I just multiply it and separate it. This problem is a limiting problem. We have a limiting process here happening. We're finding the limit as n goes to infinity of the absolute value of this. So let's now do that computation. The limit as n goes to infinity of x minus 2 times n minus 1 over n is actually just x minus 2. Right? We do this in throwing the absolute value there as well. We will do that. This is going to be x minus 2 because this piece is the only one that has n's in it. And this piece, n minus 1 over n, that limit is just 1. And 1 times x minus 2 is just x minus 2. So we simply get x minus 2 in the absolute value. And we're almost done with the problem now. So for the power series to converge, it has to satisfy x minus 2 in absolute value being less than 1. Right? That's what we have to satisfy. Which means we could drop the absolute value, or it means that x minus 2 has to be less than 1 or bigger than negative 1. Finally, when we add 2 on both sides, to find the interval convergence, we need x by itself. So we add 2 on all the sides. -1 plus 2 is 1. -2 plus 2 is 0. And 1 plus 2 is 3. So we get that the power series converges between the interval 1 and 3. But we're not done, because it could be that the power series converges at the endpoint. So we have to check each of them. So this is the interval. So we know for a fact, we know the power series converges on this open interval. But we have to still check the endpoints, because it could be that we converge at 3 or at 1 as well, or at both. So let's figure out what happens when we plug in 1 and 3. So let's check the endpoints. So for x equals 1, we have the series n equals, what is it, 1? Oh, actually it was n equals 2, that's fine. N equals 2 to infinity. I kept writing 1. The problem is n equals 2 to infinity. The series of n equals 2 to infinity of 5 times 1 minus 2 to the power n divided by n minus 1. Now, 1 minus 2 is equal to -1. So we got the series from n equals 2 to infinity of 5 times -1 to the n over n minus 1. You could factor out that 5. So this is 5 times the series of n equals 2 to infinity of -1 to the n over n minus 1. And guess what? This is an alternating series. This is alternating series. And by the alternating series test, this converges, because the denominator is going to 0 while the top is alternating. Alternating series, so it converges by alternating series test. So now we have our interval of convergence being 1 to 3 open. Okay, now we know that we converge at 1, so we close that in. Now we have to check at 3. If we converge at 3, we close that side in. If it doesn't, then that's our solution, this interval. So let's check for 3. So how about when x is equal to 3? When x is equal to 3, we have the following series. We have the series from n equals 2 to infinity of 5 times 3 minus, what is it, minus 1, minus 2 actually. 3 minus 2 over n minus 1, and this is to the n. Again, you could take the 5 out, so you get 5 times the series of n equals 2 to infinity of 1 to the n over n minus 1. And this particular series is going to diverge. This is going to diverge, because it's going to be, you could do a limit comparison test with the harmonic series. So you have 5 times the series n equals 2 to infinity. My infinities are looking more like squares today. And this is 1 to the n over n minus 1. 1 to the n is just 1. It doesn't matter what n is. So this is really 5. Go to the bottom. So this is really 5 times the series n equals 2 to infinity of 1 over n minus 1. But you could say that this is a p series with p is equal to 1, which diverges. So this is a p series with p equals 1. So it diverges. Or you could use the limit comparison test or direct comparison test even, and compare with the series. You compare with the series 1 over n, which we know diverges as a harmonic series. And you also get that divergence there. So therefore, just to answer the question answers for the interval convergence. So the interval convergence is 1 to 3, where the 1 is included and not the 3. It is very important in this problem that you check the endpoints. It's extremely important that you check the endpoints. If you don't check the endpoints, then you're going to get the problem wrong, unless the problem that you get doesn't converge at the endpoints. In that case, you'll probably get it right. But knowing the department, you probably will get either both of them converge in the endpoints or one of them will converge in the endpoints, because the department wants you to check for the endpoints for convergence. Any questions on this one? Okay, going once, going twice, and it's on. The next problem that we have up here cooking is row number 12. Yeah. Row number 12 says to find the degree 4 Maclaurin polynomial, and we're giving a function. We're given the function. The function is 3 plus cosine of x. We're also given the form of the Maclaurin series as well to check. So for this particular problem, we need to find 4 coefficients using f of x equals 3 cosine of x. Let me bring this all the way down. It's not in the way. So here we have to find the degree 4 Maclaurin polynomial for the function 3 plus cosine of x. So we have f of x is equal to 3 plus cosine of x. Now, we are told how to find the Maclaurin polynomial because we're given the equation here. That is the series k equals 0 to 4 of f to the k of 0 over k factorial times x to the k. So we're given this information and we have to use it. The first thing we will do is we will find the coefficient for x to the 0. So step number 1 is to find the coefficient for x to the 0. X to the 0 is just 1, and that's the first term of the polynomial. To do that, we simply plug in f of 0 over 0 factorial into our function that's given, that's 3 plus cosine of x. So we're looking for this piece. That's the coefficient of the x0. Right, this is x0, and this is how you find the coefficient. And also, this is f of 0, but f of 0 is just the original function. This k here represents the derivatives that you're taking. So at 0, you have the original function. When you have f of 1, that's the first derivative. When you have f of 2, that's the second derivative, and so on. Our function is 3 cosine of x. So if you plug in 0 for 3 cosine of x, you get 3 plus cosine of 0. It's important to know your sine and cosine wave because you're going to use them. There's a sine wave, there's a cosine wave. Cosine of 0 is 1. So we get here 3 plus 1, which is 4. So we have the first coefficient. So for our Maclaurin series, we have 4 times x to the 0. X to the 0 again being 1. Great, excellent. Let's move on to the second one. So to find the second coefficient, for x1, so for x1, we do the derivative. So first of all, what is f of x? F of x is 3 plus cosine of x. That was f of 0. We have to find f of 1. F of 1 is the first derivative, or f prime. The derivative of 3 is 0. The derivative of cosine is negative sine. So f prime of x is really just negative sine of x. And again, to find the coefficient of the Maclaurin series, I'm doing f1 now of 0 divided by 1 factorial. Because this is increasing with the number of the degree. Here I didn't make a mention of the 0 factorial because 0 factorial is just 1, and 1 factorial is just 1. In any case, f prime of 0 is equal to negative sine of 0 over 1 factorial. Sine of 0 is 0, so we get negative 0 over 1, which is 0. So we get that for x1, or our second term, let me show it like this, for our second term, we have 0x to the 1. That's our second term. So the third step is to find the coefficient for x squared. So now we find the third term for x squared. For x squared, we're doing the second derivative. So we have f double prime of 2 factorial of 0. Now, the derivative that we had prior was negative sine of x. The derivative of sine of x is cosine of x. So the derivative of negative sine of x is negative cosine of x. So we have negative cosine of 0 here divided by 2 factorial. Again, cosine of 0 is 1. So we have negative 1 divided by 2 factorial, which is 2. So we get negative 1/2 for x squared. So our third term is negative 1/2 x squared. 4 is for x cubed. Notice that we are doing this from 0 to 4. Okay, we're doing this from 0 to 4. So we're going to have 5 values, 5 terms, the 0 value and then 1 through 4. So we're going to stop once we get to the 5th term. So right now we're going to find the 4th term, which corresponds to x cubed. So for x cubed, you're doing the third derivative of f of 0 over 3 factorial. What that is equal to, well, what was our second derivative? Our second derivative was negative cosine, right? Negative cosine. Yeah. Now, the derivative of cosine is negative sine. So the derivative of negative cosine is going to be positive sine. So you're going to get sine of 0 here over 3 factorial. But again, sine of 0 is just 0. So you have 3 factorial, which is 0. So the fourth term is 0 times x cubed. Finally, the fifth term, not the fifth term, the fourth term, yeah, the fifth term. Finally, the fifth term, which corresponds to x to the 4, is going to be found by doing the fourth derivative, evaluating that at 0, and computing 4 factorial. Again, our third derivative was negative sine, not negative sine, sine of x. Was sine of x. So our fourth derivative is going to be cosine of x, because the derivative of cosine is, the derivative of sine is cosine. So you're going to get cosine of 0 or 4 factorial. Cosine of 0 is 1. 4 factorial is 4 times 3 times 2. 4 times 3 is 12, times 2 is 24. So we're going to get our fifth term. Our fifth term is 1 over 24 times x to the 4. And now all we have to do is put this together. So we have 1 over 24 x to the 4. We have 0 x cubed. We have negative 1/2 x squared. We have 0x, and we have 4. That's the first term that we found. The first one we found was 4x to the 0. So let me just put it all together. So we get that the degree 4 Maclaurin polynomial is the following. We get P4 of x is equal to 4x to the 0 plus 0x to the 1 plus negative 1/2 x to the 2 plus 0x to the 3, finally, plus 1 over 24 x to the 4. We could simplify this, we get rid of the values of 0. So 4x to the 0 is simply just 4, because x to the 0 is 1. 0 times x to the 1 goes away. Anything times 0 is 0. Plus times minus is minus, so we get negative 1/2 x squared. And finally, 0x cubed goes away, so we're left with x to the 4 over 24. And that's the solution to this problem. So the difficulty here is realizing that you're given all the information that you need. You actually are given all this information in the first line of the problem here. You're given the formula to calculate this, and all you have to do is find the terms one by one. To find the terms, you really only need to do is find what f of k over k factorial is and evaluate it at 0. And again, this k just represents the derivatives that you're taking. F0 is the original function, F1 is the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, and so on. Okay? Any questions on that? All righty, seeing none, our last two problems. Problem number, let me see, problem number 13, let me bring it down. And then we have problem number 14. I said I wasn't gonna do 15 and I owe you 10. So I'll send you a video for 10 a little later, probably today. And I owe you 15 as well. 15, I have to really think about it. I haven't done that problem in a while. So for this problem, we're given a Maclaurin series. We're given the Maclaurin series for e to the x. We know what that equals, and we have to use it to evaluate a function, and that function is g of x equals 2 times e to the 3x. Probably should have given myself more space in the beginning. I didn't think this problem would take so much space. I guess that they do. Moving this like this is annoying. Alrighty, this is the end. All right, so we have to use the Maclaurin series for e to the x for the function g of x equals 2e to the x. So to find what the Maclaurin series is equal to, we can do the following. So we have 2e to the 3x given. Okay, we have this given. We know what e to the x is. E to the x by itself is this. So we could do this in 2 steps. First, let's begin with the original Maclaurin series that we're given. We're given e to the x is equal to the series of n equals 0 to infinity of xn over n factorial. The first thing we could do is to make this look like this is to multiply both sides of this equation by 2. So let's multiply both sides by 2. Multiplying both sides by 2. If I multiply both sides by 2, I get 2e to the x is equal to 2 times the series of n equals 0 to infinity of x to the n over n factorial. Next, here we have 3 to the x given to us. But in our Maclaurin series, we only had x. So all we have to do is substitute 3 to the x for x and we're done. This is actually probably the second easiest problem on the exam. It looks difficult, but it's actually the easiest. This is 2e. We substitute x equals 3x for x. So we're going to have 3x is equal to 2 times the series n equals 0 to infinity of 3x to the power n divided by n factorial. And believe it or not, this is the solution. You could separate it a little bit if you want to make it look nice. You could write this as 2 times e 3 to the x is equal to 2 times the series n equals 0 to infinity of 3 to the n times x to the n. You could do this, and it'll look a little prettier if you do it like this, but this is the solution right here. This is probably the second easiest problem on the exam. So if you remember the steps to do this and you get a problem similar to this one, I suggest you begin probably with either this problem or problem number 10. 10 is actually not too difficult, neither is this problem. As you see, all we did was we asked ourselves, how can I make this given information look like this? We began with a e to the x on the left side. To make that e to the x look like a 2e to the 3x, we multiply both sides by 2. We're allowed to do this in an equation. And then to make x look like 3x, we simply substituted x literally with 3x. And we get the Maclaurin series for 2e to the 3x. Are there any questions on this one? All right, seeing none, I will do the last problem that we have cooked up for today. That's problem number 14. And that is another really nice problem that you could get, which we have to use integration on a Maclaurin series. Let me just bring this all the way down. I wish there was an easier way for me to like scroll down. And the problem disappeared. Yes, of course it did. And I think I could just put it on the side as well, but it's a bit annoying. Alrighty, so the last problem that I will do is this one. So integrate the Maclaurin series that's given, and the one that's given is 1 over 1 plus x is equal to the series from n equals 0 to infinity of -1 to the n times x to the n to find the Maclaurin series for the function L of x equals 1, ln of 1 plus x. Here, we're going to use term by term integration, and that will help us find the Maclaurin series. So first of all, let's look at the Maclaurin series given here. This is 1 over 1 plus x being equal to the series n equals 0 to infinity. What we're going to do is we're going to write out some of the terms of this side here. So this is supposed to be an x. So what do we get? We have 1 over 1 plus x equals 0 to infinity, -1 to the n, x to the n. So if you plug in 0 here for n, you're going to get -1 to the 0 times x to the 0. If you plug in 1, you're going to get -1 to the 1, x to the first. If you plug in 2, you're going to get -1 to the 2, x to the 2. X to the 2. If you plug in 3, you're going to get -1 cubed, x cubed. If you plug in 4, I'm going to stop at 4. I'm going to get -1 to the 4, x to the 4. You could simplify that a little bit. You get 1 over 1 plus x is equal to the series is n equals 0 to infinity. -1 to the n, x to the n, which is equal to 1, because this piece becomes 1. -1 to the 0 is 1, x to the 0 is 1, so that's just 1. -1 to the first is -1, and -1 times x is x, so we get -x. -1 squared is just +1, and +1 times x squared is just x squared. -1 cubed is -1, -1 times x cubed is -x cubed. And for x to the 4, and this continues on. For x to the 4, we get plus x to the 4, because -1 to the 4 is 1, and 1 times x to the 4 is x to the 4. And you will see what the next term will be if you follow this part. It's going to be -x to the 5 plus x to the 6, and so on. So that's what we get when we have when we get this when we expand this series. Now we're saying that this is equal to this, which in turn is equal to all of this. By transitivity, this means that this piece is equal to all of this piece. So we could write this as 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus x to the 4 minus x to the 5 and so on. Now what we could do is we could integrate both sides of this equation term by term. So I could take the integral here on this side, the x, and then I could take the integral for each of these pieces. I could take the integral for each of these pieces. Now the integral of 1 over 1 plus x dx, you could just use substitution for that one. You could do 1 over 1 plus x dx. Let u be equal to 1 plus x. That means that du is equal to 1 dx, which means that you have the integral of 1 over u du. But this is just ln of u plus c, which is just ln of what u was, which is 1 plus x plus c. So that's the integral on the left side. I'm going to forego writing the plus c on this part because the plus c is going to cancel out with the plus c on the other side. So there's going to be ln on the left side of 1 plus x, right? That's this piece. This is equal to the antiderivative of each of these independently. So the antiderivative of 1 dx is just x by the reverse power rule. And the antiderivative of x is x squared. The antiderivative of x squared is x cubed. So this is what we're getting. We get x cubed here. The antiderivative of x cubed is x to the 4, right? And I'm just writing this like this, but obviously you're going to write it like this, over 2 over 3 over 4 by the power rule, then plus the antiderivative of x to the 4 is x to the 5 over 5 minus, the antiderivative of x to the 5 is x to the 6 over 6, and so on. And this, believe it or not, is what ln of 1 plus x is equal to, right? So now we were able to actually use integrate this Maclaurin series. Now all you have to do to finish the problem is figure out the pattern here, right? Because at the end of the day, we were asked to write a series, and this is just an expansion of a series, but it's not. This is not what gives us the expansion. Notice here that the signs are alternating. Okay, so the signs here are alternating. We begin from n equals 1 to infinity, because it's an infinite series, and the signs are alternating. So we have -1. Now the first sign is positive. If the first sign is positive, that means that we're going to begin at n plus 1. Because if we begin just at n, then it's going to be negative, because n begins at 1. So we have to do n plus 1 so that we begin with a positive term. So we have n plus 1 in there, and then every term has an x in it, right? And that x is actually just to the power n, because this is x to the 1, x to the 2, x to the 3. And again, we're beginning at 1, so if you put x to the n, they begin at 1, then go 2, then 3. And then this is divided by what? This is divided by 1, 2, 3, 4, 5, 6, or by n itself. And that is the Maclaurin series for ln of 1 plus x. And the way that we found it, again, was by taking the given information, expanding the series. This is a key step right here, expanding the series given, and then doing the integration of each piece. So you do the integration piece by piece, and then we use that information to obtain the pattern that we got down here. This is probably one of the most technical problems on the final. You have to do some thinking here. You have to find a pattern for your problem, but it's not necessarily a hard problem. If you understand how Maclaurin series work, It's not that difficult. And the problem tells you what to do. It gives you the Maclaurin series. It tells you to use integration. So all you really have to do at the end is write out the pattern. Are there any questions? That was the last problem that I'm gonna do for problem number 15 and problem number 10. Especially for problem number 10, I'm gonna send you that solution once I finish writing it down. This review was recorded, so I'm gonna upload it to YouTube today, to our YouTube channel, and I will send you all an email once it's posted. In fact, I'll send that email to every single Calc 2 student in case anybody missed the review today.
I just have a few questions
Thank you for
after
joining today.
Professor.
Good luck on your finals, especially for those of you who have your final tomorrow. You only have, less than probably 24 hours to study. So good luck, everyone.